Hey there, I'm now back to finish up page 5 of 3.2 and do a little bit of page 6. So for example 5, we're being asked to find the symmetric difference quotient for f prime 7 when f of x equals 2x cubed minus 9x squared plus 13. So the symmetric difference quotient is right up here. And it's basically just going to be f of a plus 0.01 minus f of a minus 0.01 divided by 0.002. So what I'm going to do to find f of prime 7, and I'm going to put a little squiggly lines as an approximation, is I'm going to do f of 7.001 minus f of 6.999 over 0.002. Now you could plug in 7.001 into this function as well as 6.999. See what you get, subtract and divide by 0.02. There's your symmetric difference quotient. But just to save a bit of time, I'm going to actually pull up this calculator app called Wabbit. And fortunately I have it working now, which is good. I'm going to go to y equals. I'm going to clear these functions. And I'm going to punch in 2x cubed minus 9x squared plus 13. I'm going to quit. Go alpha, trace, select y1. So we choose like function notation. And then alpha, trace, 6.999. So you get that, and then divide that by 0.002. So this is probably more efficient than just trying to plug in 7.01 to 2x cubed and plug in a 9x squared. To do it individually, I think would take too long. So we get 168.002. Now, if I actually do the numerical derivative, I will get the same thing. So in the first video, I didn't have this Wabbit app, so hopefully you're able to understand my instructions for finding the derivative in the calculator, but now you actually get to see it. So we go alpha window, option 3, and we're going to do the function, which is 2x, well actually, that's silly. Silly Wabbit. Sorry, I couldn't resist. So you have y1, delete, because I already have it defined, so why did I even need to type in the function again? And that was not intentional, I just was organic when I said silly Wabbit. Anyway, we get 168.002. If I do nderiv, the numerical derivative in the calculator. And I can't write right now. I think I'm just a little bit too excited for the Giants game about to start. So there we go. Example 6. They're asked to graph the nderiv of f of x equals x cubed. So if I put x cubed here and just graph it, we should know how that graph looks. Now, if I want to graph the derivative, I can go to y2, do nderiv, x, alpha trace y1, and you're going to have to do x equals x. You don't want to put a number there. You need to put x equals x because you need to find a derivative for all x values. Otherwise, if you put a number, say x equals 5 or 4 or whatever, the calculator is just going to evaluate the value of that derivative and then graph a horizontal line because when y equals a number, it's just a horizontal line. So you don't want the derivative to be evaluated for a number, but for just x. And you can see the derivative is about to start. It takes a little while because it's calculating it. So we see how it just looks like a parabola. So we'll go back here. And we know it's just y equals x, 3x squared, because we've actually done this many times now. So we expect it to be a parabola. And also, it kind of makes sense because right in the beginning, when the interval from negative infinity to 0 for x, we have positive tangent lines, and at x equals 0, we have a horizontal tangent line, and from 0 to infinity, we have positive tangent lines. So that's what happens there. This function we've graphed before. I actually graphed in the first page of the notes. So let me actually redraw that. So that's what we have. And we're asked to find the numerical derivative at x equals 0. if I use the calculator, let's go back to the home screen, alpha window, option 3, x, and then absolute value, you can find alpha window right there, x, divide by x, oops, divide by x, try to do x equals 0. The calculator says the answer is 1,000. So it says it's 1,000. But we know it's D&E because the left-hand derivative, which I know is, or actually it's not continuous, so it's not differentiable. Let me take that back. Not continuous leads to not being differentiable. So what's happening is the calculator, when it does numerical derivatives, calculates symmetric difference quotient. So it's doing, f of 0.001 minus f of negative 0.001 divided by 0.002. And it gets us 1,000. So, but we know that's not true because we know it's not differentiable since it's not continuous. Okay, last example. We're going to talk about f of x equals x minus 3 to 2/5. And we're going to try to determine the reason for it not being differentiable. But first we have to prove it's not differentiable. So if I were to graph this, and we'll go back to the calculator. So I'm going to type in x minus 3 raised to 2/5. And I'm actually going to leave y2 alone because I want the derivative of y1. So it's kind of nice to be able to know to define things as different functions, like I know how to access all the different functions like alpha trace. You kind of see it all right there, so you can pull up any function you want. So if I graph, I'm going to see the original function first. Okay, and the derivative is going to take a while, so I'm going to actually just graph the original function here. And I did not lie. Now the derivative graph is coming. See how it takes a long time? And it looks like there's a vertical asymptote at x equals 3. So it definitely looks like we have a rational function here, or something kind of like that. Or a graph looks like that for the derivative graph. And we have a cusp. And what's happening is that, first of all, f of x is continuous at x equals 3. F of 3 exists. The limit as x approaches 3 of f of x also exists. And both of these equal 0. So, of course, f of 3 equals the limit as x approaches 3 of f of x. So we got a lot of good stuff here. So we know it's continuous, but then when I evaluate the slopes of the tangent lines, as I get closer and closer to 3, we notice that there's negative on one side, positive tangent lines on the other side, and it starts getting more steep as we get closer and closer to 3, which kind of shows why we have our the values of our derivatives when we get close to 3, either going towards negative infinity or positive infinity. So our left-hand derivative is negative infinity at x equals negative 3, and our right-hand derivative, sorry, positive 3, not negative 3, my bad. It's positive infinity. And when that happens, we get a cusp, as we discussed, I think, in page 3 of the notes. So we will definitely look at this in more detail later in chapter 3, but at least we can graph it and identify the reason for its non-differentiability. And that concludes the video. Oh, and lastly, go Giants.